previous video, we introduced here is the formal definition of a limit. Now, let's actually use the formal definition of the limit to to rigorously prove certain limits are what we think they are. So let's use, as a first example, let's take a look at, let me get my notes here. Let's take a look at the limit as x goes to 3 of, let's say, 6x minus 4. So what we want to do is, let me put some parentheses here. So we know that this is a continuous function, so we can just substitute in. So the answer we can just say is going to be 6 times 3 minus 4 is 14. So you want to prove this with epsilon delta. So the standard way to say this, would be give an epsilon delta proof that the limit as x goes to 3 of 6x minus 4 is equal to 14. Okay, so this might seem scary. How are we going to do this? Well, what we want to do is that we're going to work backwards here. So our goal is we want absolute value of f of x minus L to be less than epsilon. So that's always going to be our goal. So here, let me get them both on screen at the same time here. This is the goal that we're aiming for. Absolute value f of x minus L has to be less than epsilon. Now, any given problem, our f of x and L are going to be different. And so in this problem, we see that f of x is 6x minus 4, and L is 14. So really what we're saying here is that we want 6x minus 4 minus 14 to be less than epsilon. So let's just manipulate this a little bit. So this would be equivalent to saying that 6x minus 4 minus 14 is 6x minus 18 is less than epsilon. So our goal has become, we want 6x minus 18 to be less than epsilon. And the question is, how do we choose x so that 6x minus 18 is less than epsilon? Because the thing that we're allowed to have is we can choose delta such that absolute value x minus c is between 0 and delta. So this part up here, this part above the line, this is what we want. Whenever I teach this stuff, we always kind of list out what do we want and what do we have. And so the thing that we have is we have that absolute value of x minus c is less than delta. That's the equivalent of this line up here. This is always what we want. This is always what we have. This is always what we want. This is always what we have. But now our thing is that we have to say, well, in this particular problem, what do we have? Well, in this particular problem, there is c. c is equal to 3. So the thing that we have in this particular problem is that x minus 3, the absolute value of that, is less than delta. So we write down what we want, we write down what we have, and we attempt to relate the two of them together. So if I was teaching this live in class, I'd pause here for a few seconds and ask for a volunteer to see, how do these two expressions relate to each other? And so the thing to realize here, well, what happens if we factor? What happens if we factor this expression here, and we factor 6x minus 18? Well, there's a 6 both places. So what we want is absolute value 6x minus 18 is less than epsilon, we can pull out a factor of x here and say, sorry, a factor of 6 there, to say 6 times absolute value x minus 3 is less than epsilon. And so now we see here that the absolute value of x minus 3 is, what do we want that to be? We want that to be less than epsilon over 6. Once again, I'll remind you, what do we have here is that absolute value of x minus 3 is less than delta. So these two are both, in both of these expressions, we have absolute value of x minus 3 equal to something else. But the thing is, we're told what epsilon is, and we can pick delta to be whatever we want it to be. So, what's the obvious choice here for delta? If we're told what epsilon is, choose delta equal epsilon over 6. So whatever value you choose of epsilon, I'm just going to pick delta to be that value of epsilon divided by 6. And now in that case, that will, if we have this, then we'll get this, which can reverse engineer everything all the way back up. So what does our formal proof look like here? We would say let epsilon be greater than 0. So we're supposing here that epsilon's given to us. We're going to say choose delta equal to epsilon over 6. Then, if the absolute value of x minus 3 is less than delta, which is epsilon over 6, we see that the gap condition, which is 6x minus 18, that's equal to 6 times x minus 3. So this is less than 6 times epsilon over 6 from this line right here, which is epsilon. And so we have exactly matched here what is the formal definition of the limit. So we can, maybe I should write down the conclusion. So we conclude that the limit as x goes to 3 of 6x. So I should have written, I'm realizing I made one little thing here that was not too good. I'll explain what that is in just a moment here. So the thing I should have written here was one more preliminary step, which is we want this to be 6x minus 4 minus 14, because this is f of x minus L. So what do we want? We want the absolute value f of x minus L to be small. F of x is 6x minus 4, L is 14, so that's 6x minus 18. So let's just see how this goes through with our formal definition of the limit. That limit as x goes to c of f of x is equal to L. The limit as x goes to 3 of 6x minus 4 is equal to 14. If for every epsilon greater than 0, there is a delta. There is a delta. In particular, we're choosing delta to be epsilon over 6, such that if x minus c, x minus 3, the absolute value of that is less than delta, then the absolute value of f of x minus L is less than epsilon. The absolute value f of x minus L is less than epsilon. So this is how, if you tell me this is how small we want our gap condition to be, this is how close on the x-axis we have to shrink things. Going back to this picture here. You tell me how small, how close to the limit we want our output to be, I'll tell you how far along on the x-axis you have to go in order to make x sufficiently close to 3. So just to do this in a couple of examples here, so if we were to say here, if epsilon is equal to 0.01, then delta would be 0.01 divided by 6. So that is you're given epsilon greater than 0, here's how close you want to choose things. If we choose epsilon to be 0.000001 and we want to be really, really, really small, how close do we have to get? Choose delta be 0. Let's see, that's 6 zeros and a 1 over 6. So this is how, no matter how small you choose epsilon, we can find a delta. No matter how small we want our gap condition to be, we can find a value of delta that will make x sufficiently close to c, in this case 3, so that we satisfy the gap condition. So this is a pretty typical example of how we write things out.